Hello, my name is Jaden Feng, and today I'll be doing a talk on semantic and engineering knowledge-based embeddings for maintenance work order clustering. For many organizations across many domains like defense, mining, and manufacturing, asset maintenance is a multi-million-dollar task. It is essential for the maximizing runtime productivity of assets and minimizing repair costs and threats to human safety in the workplace. An essential data source in industrial maintenance is the maintenance work order. Whenever a piece of equipment or an asset fails or has work performed on it, a maintenance work order is written up by the maintenance technicians or the equipment operators who observe the failure to keep a record. Maintenance work orders capture important information about an actual or impending failure event and the condition of the asset. This includes the manner in which the failure occurred, known as the failure mode, where it occurred, and any maintenance actions performed. You can think of maintenance work orders as a health record for assets. The accurate analysis of maintenance work orders is vital for developing effective maintenance strategies and improving asset management. To help facilitate this, a maintenance professional manually assigns a failure mode code from a predetermined list to the event described in the work order. For example, the failure mode code CRK for cracked hydraulic pipe. After failure mode codes have been assigned, it is then used as an important data source for failure mode and effects analysis, where engineers identify the function for each asset component and all their potential failure modes, failure causes, and potential failure effects, and from these insights improve maintenance strategies, activities, and designs. Now, despite existing standard failure mode code lists, such as ISO 14224 for the oil and gas industry, there are no standard set of failure mode codes specifically made to represent failures that happen in the maintenance industry. As a result, when used in maintenance, these lists often suffer from having too many codes, making them confusing and time-consuming to use, or have codes that are too general to be useful for analysis. Thus, many organizations use their own failure mode code lists developed internally by domain experts. As a result of that, however, there is an inconsistent coding within companies and across industry, limiting benchmarking, failure trend analysis, and information exchange. Which leads us to our big problem, that there is no standard set of generic failure mode categories that can be used for industrial maintenance. While there are no standard lists of generic failure mode categories, we do have a generic standard for industrial assets and equipment, IEC 81346. It provides a classification scheme for the inherent functions of objects, including sensing objects with the inherent function to sense things for objects that pick up and represent information, storing objects that store things for later retrieval, or protecting objects that protect against damage or other undesirable states. And lucky for us, there is a dataset of maintenance work orders that is annotated according to IEC 81346. MAINT is the largest annotated maintenance work order dataset with entities for physical objects or equipment and failure modes in the form of undesirable states, processes, or properties. Engineering knowledge in the form of inherent function is included for every physical object entity within the annotation classes. Another form of engineering knowledge is contained in the relations between physical object or failure modes. The has part and has patient relation can help identify which equipment and inherent function is the most relevant to the failure mode in a work order, which in this case is the sensing object thermostat. So the research question we are trying to answer is, how can we use the semantic and engineering knowledge in maintenance work orders for creating a set of generic failure mode categories? In order to create a generic set of failure mode categories, we have to be able to group similar maintenance work orders together. There are two types of clustering algorithms tested in this study, k-means and agglomerative hierarchical. K-means is where a predetermined number of centroids are placed on a vector space, and each item that is closest to a centroid is considered part of that cluster. The algorithm iteratively moves the centroids around the vector space to find good clusters that maximize the similarity within clusters and the dissimilarity with items outside of the cluster. Agglomerative hierarchical is where each item starts off as a cluster of one. Then the algorithm proceeds to join the most similar clusters together, and repeats the process until there is one giant cluster containing all the items. The process can be halted at any time when the desired number of clusters are remaining. Now, there are some challenges when performing clustering. The first one is that we don't know the number of clusters that exist within the dataset. With unsupervised clustering, a common method to determine the number of clusters is to perform clustering at different number of clusters and plot out their silhouette score. Silhouette score is a metric for the quality of clusters being produced by calculating the similarity of members within the cluster and the dissimilarity with non-members. The closer to 1, the better the silhouette score, but the smaller your clusters get, that's the trade-off. Another way to determine the number of clusters is through the dendrogram produced during hierarchical clustering. Both of these were considered while deciding on an optimal number of clusters. The second issue faced during clustering is that the main-T dataset is small and unbalanced. There were two main-T datasets that were combined for this research, main-T Gold and main-T Silver. In main-T, there is an uneven distribution of inherent functions, as shown in this graph. In order to combat this, synthetic data generated from a fellow honors student's project, also based off main-T, was introduced to the dataset. The project, titled Generating Authentic Grounded Synthetic Maintenance Work Orders, is done by Alison Lau, who will be also doing a presentation on her research. The generated synthetic work orders were added, ignoring any work orders that had to do with the inherent functions guiding and holding, to lessen the skew of the dataset. All work orders to do with the inherent function information processing were also removed from the dataset due to the small number of work orders even after adding the synthetic dataset. Maintenance of information processing equipment are generally outsourced to external maintainers who have their own separate records and are maintained following a fixed schedule. Both of these result in companies not producing a work order for its maintenance work, and thus is unlikely to occur in the context of the maintenance industry. Another observation from prior analysis of the main-T dataset was the frequent occurrence of the failure mode leak and its variants like leaking or leaks. This also caused a skew in the dataset in terms of failure mode words in the maintenance work order. And so the synthetic data generated that included the word leak or similar was not added to the dataset. Now, in order to perform clustering, we need some way of measuring the similarity of different maintenance work orders, which is achieved through creating sentence embeddings. What are sentence embeddings? They are a numerical representation of a sentence, in our case a work order description, consisting of a vector of numbers that capture different features of that sentence. Sentences that are more semantically similar will be closer to each other in the vector space, while sentences that are very different will be far apart. When creating sentence embeddings for maintenance work orders, we encounter a few challenges. Firstly, off-the-shelf embedding methods trained on general domain language datasets are not good at representing technical texts. Maintenance work orders are filled with engineering jargon, acronyms, abbreviations, misspellings, and colloquialisms that are not common outside of an engineering context. Secondly, semantic and syntactical representations of maintenance work orders alone are not sufficient to capture the engineering knowledge of the relationships that exist between equipment, their inherent function, and failure modes. Thus, it is important for this task to incorporate the engineering knowledge from main-T annotations into the sentence embedding itself. The method we use to create sentence embeddings takes inspiration off a previous work that trains a convolutional neural network off a semantic embedding as the input and a statistical representation of the sentence as the output. The hidden layer was taken as the new sentence embedding. For our experiments, we have two new embedding methods. For both, instead of a statistical representation as the output, our models were instead trying to classify the maintenance work orders by inherent function. The general idea with this feature extraction technique is that the model, while performing a classification task, can identify patterns between the semantic representation and the inherent function, and capture that relationship within the embedding. Thus, the final sentence embedding being produced should incorporate the semantic meaning of the words as well as the inherent function of the work order. We ended up focusing on two different embedding methods. The first method accepts word-to-vec embeddings as the model input, to a by LSTM model and predict the maintenance work order's inherent function. Meanwhile, the second method uses sentence BERT as the input, which was then trained to predict inherent function in a neural network. Both of these methods resulted in sentence embeddings of dimension 10, which was the size of the hidden layer. This is a hyperparameter that can be changed. Altogether, in our experiments, we had 4 sentence embedding approaches. The first 2 approaches uses off-the-shelf embedding methods without introducing any engineering knowledge. The first is getting word-to-vec vectors for each word in the maintenance work order and then averaging them. The second is a sentence BERT embedding. The last 2 approaches are the word-to-vec by LSTM and the sentence BERT neural network approaches mentioned earlier. The clustering approaches tested were k-means, average agglomerative hierarchical clustering, and ward agglomerative hierarchical clustering. Every combination of embedding and clustering approach was tested in this study. Due to time constraints for this presentation, only results from average hierarchical clustering will be discussed today. Clusters were evaluated and analyzed in 3 ways. First, manual analysis on each cluster by subject matter experts with an engineering background. Second, statistical data on cluster shape and properties. And third, normalized mutual information score. I will be going through each of these as I go through the results for average hierarchical clustering. First, clusters were analyzed by subject matter experts with engineering knowledge. This table shows the results of the word-to-vec by LSTM embedding approach. It was determined that a good cluster has a majority, more than 80%, of work orders with a restricted number of inherent functions, between 1 and 3. For example, over 80% of work orders in cluster number 8 have the inherent function driving, protecting, and transforming. By looking at the top failure modes and the equipment in this cluster, we can see that this cluster has grouped together maintenance work orders to do with leaking oil and similar work orders. Meanwhile, cluster number 1 seems to purely be any emitting object failing to emit. Then, further analysis was performed on bad clusters to determine why those work orders were being grouped together. This provides insights into hidden patterns within clusters captured by the sentence embedding and reveal features or aspects that are yet to be considered for future feature extraction. It also helps finding underlying reasons for unhelpful clusterings, like grouping together a specific equipment or a reoccurring inconsequential phrase such as left-hand side. In this case, cluster number 4 was determined to be grouping maintenance work orders if they contain general feature mode terms such as unserviceable, not working, or faulty. Meanwhile, cluster number 9 was found to be grouping failure modes that were material in nature, such as seen in the top failure mode words, such as the word crack, worn, missing, and leak, all being semantically similar. The second method of evaluation is analysis based on statistical characteristics, such as mean, median, minimum, and maximum number of documents, and the distribution of inherent functions across clusters. These were calculated to provide a comparison of different embedding methods. Each column is a different embedding approach. For the last 4 rows calculating the distribution of inherent functions across clusters, they are checking what percentage of the dataset belong to a good cluster, which, as a reminder, is a cluster consisting of work orders of largely the same inherent functions. These 2 rows return the percentage of clusters that are good clusters, while these 2 rows return the percentage of documents belonging to these good clusters. Something that becomes apparent is that despite the percentage of clusters being in somewhat the same range across all embedding approaches, the first 2 embedding approaches have a drastically lower percentage of documents in good clusters. This is due to the tendency of creating many clusters that have very few documents in them, and they end up with 1 or 2 very large clusters, as reflected in the maximum number of documents being much larger than the latter 2 approaches. This suggests that the semantic representation alone is having difficulty with the technical meaning of the text, and not capturing enough expert information to meaningfully cluster work orders. These results are unlike the latter 2 approaches, which almost always returned a higher distribution of clusters and documents in good clusters. And thirdly, normalized mutual information score was used to measure the similarity between clusters and maintenance work orders that were grouped solely by inherent function. When calculating NMI, the number of clusters was always set to 16, which is equal to the number of inherent functions in the dataset. This gives an idea as to how much inherent function as a feature contributes to the final embedding. If inherent function was a very strong feature, the resulting clusters would be very similar to maintenance work orders that were grouped solely by inherent function and thus would return an NMI of close to 1. The NMI scores reflects the strength of expert knowledge captured within each embedding approach. It also shows how semantic representation alone is insufficient to capture the engineering knowledge in maintenance work orders, with low scores for both average word-to-vec and sentence-BERT approaches. So, to recap this study's contributions, the aim was to create a set of generic failure mode categories for the maintenance industry. Through this study, we were able to create embeddings that combine a semantic representation of maintenance work orders with engineering knowledge in the form of inherent function annotations. From these embeddings, we were able to perform clustering to group similar work orders together, and by analyzing the resulting clusters, identify the good clusters that can be used as a generic category for failure modes. We identified 9 generic categories from good clusters listed here. Some example descriptors include guiding objects with material or structural failures, and generating or restricting or transforming objects having no charge, and driving or protecting objects that were leaking. From the bad clusters, we still gain important insights into other potential forms of similarity in maintenance work orders beyond the inherent function, and have narrowed down and grouped work orders together for further analysis. There were some limitations with this research that can be further explored in future works. One such limitation is how the identified generic failure mode categories do not cover all inherent functions. This is due to the unbalanced and skewed dataset that was used, which impact was only partially reduced by the introduction of synthetic data. Repeating the experiment with a dataset that is more balanced in inherent function, equipment type, and failure mode terminology would help to cover these sparser areas. Another potential future work is to make use of other engineering knowledge in Main-T annotations, specifically the annotations a level lower than inherent function that provides function subclasses. This more specific annotation can provide more data on similar work orders, though there may be challenges with the larger number of inherent function subclasses. Another future work is to experiment more with the architecture of embedding method. This study experimented with bi-LSTMs, convolutional neural networks, and simple neural networks. More experimentation with hyperparameters and layers can be done to improve how well embeddings are capturing the patterns between semantic representation and engineering knowledge. Another future work is to conduct the clustering over similarly annotated datasets over other domains beyond the maintenance domain. And we've come to the end of the presentation. Thank you so much for listening. See you next time.